So we were just trying to complete this chapter where we have studied the random numbers and the properties of random numbers and the statistical testing procedures in order to test if a random number sequence satisfy the important properties of random numbers. And what were these important properties? A pseudo-random number sequence is expected to conform to the properties of uniformity and independence. And we have covered everything related to the uniformity property, and we have learned how to perform hypothesis testing to check the uniformity of a random number sequence. Now, the next part is to test the independence of the random numbers in a pseudo-random number sequence. So actually, this is a much wider application than uniformity check. So we are just going to learn it partially. And our objective here is to check if there is dependence between the consecutive numbers in a sequence of random numbers. And as an example, I want to show, we have these 30 so-called random numbers because, I mean, there's a sign here which indicates that these are actually not random numbers, because what we expect from random numbers also to have a high resolution. After the decimal point, we only see 2 decimal digits here. So, our objective here is to check the dependence or independence of this random number sequence. We expect an independent behavior in the generation of these random numbers. So, starting from our first random number here, we are moving to the last, and can we really say that this sequence is an independent sequence of random numbers? Now, when you check the generation of every next number, there is not a usual pattern here. So, conditioned on the previous number here, the next number can sometimes be greater, sometimes can be less than the previous number. So, there is not a statistical dependence here, but if you check carefully, every fifth number here, so the fifth number, which is 0.89, and the 10th number, 0.93, 15th, 20th, 25th, and 30th number. So at every fifth number, we observe a very large number, which is very close to 1. So actually, this is a kind of dependence that we need to discover in the random number sequence, and such dependence is not a desired thing in the random number sequence. Now, for example, if you use these sequence in a simulation, for example, if you use them to identify the inter-arrival times of the clients into a bank, this means that every fifth client is just going to arrive after a very long amount of time after the previous client. So because of that reason, we do not want to have such dependent structures. And of course, to prove that a statistical dependence exists in a random number sequence, it would be very hard with short random number sequences. If we really want to show that a random number sequence exhibits dependence, then the test must really be performed over a long random number sequence. Now, how can we discover these dependence behaviors or dependence within a random number sequence? Remember now, actually, what we want to show is that the random number sequence has an independent behavior. Now, if you cannot discover any dependence, then this means you can safely use that random number sequence as a raw material in your discrete event simulation model. Now, one basic approach is to estimate rho IM, okay, the autocorrelation rho IM. So what is rho IM? It is the autocorrelation of every n number starting with the ith number. Now, actually, we have a very long sequence of random numbers, assuming that. Now, let's just say I am starting from the third index of my sequence and stepping forward 5 steps ahead. So m is 5. So starting from third index, at every fifth random number, I create a subsequence of R3, R8, R13, R18, so on and so forth. So this subsequence is the subsequence created starting by the ith index, and we are moving ahead at every nth index. Now, our objective is to check the autocorrelation within these subsequences, if there exists a dependence structure between every fifth number starting from the third index. Similarly, we can check the autocorrelation of the subsequence starting from the fourth index and moving ahead with a step of 3. So this is the subsequence that is studied, R4, R7, R10, R13. And here we are basically checking the autocorrelation of row 4, 3. Okay. Now these autocorrelations should be statistically insignificant, which means they should be estimated very close to 0. So we can say that there is not a significant proof to have any statistical dependence here. Now, another autocorrelation estimation can be for the original sequence itself, which is row 1, 1, right? So we are starting from the first index, and we are just moving one index ahead at every time. And the subsequence that is created here is the original sequence itself. So if you check row 1, 1, row 3, 5, row 4, 3, and every possible autocorrelation for such regular subsequences, then if every subsequence passes the test, then you can say that the random number sequence do not show any independence. Of course, this is an infinitely long procedure, as you can imagine. We are just going to discuss that point as well. Now, at this point, let's just stick to row 1, 1. Okay, so we are just looking at if there is a dependence within the regular sequence itself, if the consecutive numbers are dependent on the previous numbers. So in order to determine that, we need to check row 1, 1. And let's just say the autocorrelation test is applied and the autocorrelation estimate is very close to 1. So what does that mean? Now remember, every correlation statistic can be a real number between -1 and 1. And what does that mean if it is very close to 1? This means the subsequence exhibits positive autocorrelation, which means the subsequent numbers are too close to each other. So just like in the sequence, as you can see, every next number is just very close to the previous number. If you observe such a situation, then the autocorrelation will become close to 1. Now, if row IM, if the autocorrelation is very close to -1, in that case, we say that the subsequence exhibits negative autocorrelation, which means the subsequent numbers are far from each other. So just like in that example. So we have a very large number, then small, then large again, then small again. So we do not want any of these situations. We actually see a practical independent sequence, right? So what we want from the autocorrelation of that subsequence is to be close to 0. In that case, if the autocorrelation estimate is close to 0, then we say that the subsequence does not seem to show any dependence relation. But actually, we want all of these autocorrelations to be very close to 0. Okay, so we actually need to test all possible autocorrelation for all proper subsequences, regular subsequences. So row 1, 1 is the autocorrelation of the original sequence itself. Row 1, 2 is the autocorrelation of the subsequence starting from the first index and moving 2 steps ahead. And row 1, 3 means starting from the first index, we are moving ahead to every third index. So row 2, 1 means what? It means starting from the second index and moving 1 step ahead every time. Actually, we do not need to test row 2, 1 if we have already tested row 1, 1. Because the subsequence starting from the second index and moving 1 step ahead is already covered by the original sequence itself. But we definitely need to test row 2, 2 starting from the second index, moving 2 steps ahead every time. So R2, R4, R6, R8, so on and so forth. So basically, some of these autocorrelations should not be tested. Why? Because a larger sequence which covers that sequence as a subsequence is already tested for independence and it may have passed. Therefore, we do not need to check all of these autocorrelations, but still, this is just an infinite procedure. As you can see, this goes, the autocorrelations that we can create with proper subsequences can go infinitely many, right? So for all of these autocorrelations, what we want is all of them to be very close to zero, and we need to check this statistical hypothesis testing, and we should say that for any subsequence that starts from the ith index and moving m step ahead every time, the autocorrelation is equal to zero at null hypothesis, and it is different from zero at the alternative hypothesis. And if we cannot find any statistical proof to correct the alternative hypothesis, then we can say optimistically that there is not a statistical proof for dependence. So we need to run this hypothesis testing, but this is a problem. There are too many autocorrelations here to check with this hypothesis testing procedure. And actually, this is a dangerous operation. Why? So let me explain why we should not check all possible autocorrelations for all possible proper subsequences. Now, you see, in every hypothesis testing procedure, there is the probability of rejecting the null hypothesis while null hypothesis is true, right? Actually, this probability exists because you are defining a significance level, right? So depending on your choice of the significance level, so let's just say it is 0.05, there is a 0.05 probability to reject the null hypothesis while null hypothesis is true. Now you see, if you perform autocorrelation test with this null hypothesis, even though the random numbers in the sequence are totally independent from each other, there is a 0.05 chance to reject the null hypothesis, okay? So even though the sequence is independent, you can still reject the fact that it is independent. And if you perform this hypothesis testing procedure for 10 subsequences, for all of them to fail to reject the null hypothesis, is just going to have the probability of 0.95 to the power 10. Now, the probability that an independent sequence passes the test is 0.95, right? So failing to reject the null hypothesis has the probability of 0.95, and for all 10 hypothesis testing procedures to fail to reject the null hypothesis has the probability of 0.95 to the power 10, which is 0.60. In other words, if you apply 10 independence tests for different proper subsequences, okay, even though the sequence is totally independent, if you perform so many hypothesis tests, at some point one of them will reject the null hypothesis. So therefore, the golden rule here is do not go fishing for autocorrelation. I mean, if you go fishing for autocorrelation, at some point for a given proper subsequence, you will identify it. So if you perform this test too much, at some proper subsequence, you will eventually going to discover a dependence structure where you reject the null hypothesis. Now, we need to teach how this autocorrelation test is going to be performed. Now, this is the steps that we need to follow if we want to apply the autocorrelation test for any subsequence starting from the ith index and moving m step ahead. So it says identify the largest integer m such that I plus m plus 1 times m is less than or equal to n. Actually, you can easily solve this inequality by taking I to the right-hand side and m in the division in the denominator of the right-hand side, and you can also take this one to right-hand side. It says identify the largest integer m which is less than or equal to the values on the right-hand side. So you need to identify these inequalities, the solution of this inequality for capital M, and you need to identify the largest integer m, okay? So after that, you are going to multiply the I plus k mth index of the random number sequence with the I plus k plus 1 mth index, okay? Yeah, basically, you are multiplying every consecutive number in the subsequence. Okay, so if your subsequence is, for example, R3, R8, R13, R18, so on and so forth, you are multiplying every consecutive number in the subsequence. You are multiplying R3 with R8, then R8 with R13, then R13 with R18, according to this summation. And then you are going to divide this summation to m plus 1, because there are m plus 1 terms here in the summation, as you can discover. So basically, you are taking the average of these products, and then you are subtracting 0.25 from the value. Now, you see, if the random numbers in the sequence are independent from each other, then each of the random numbers in the sequence will have the expected value of 0.5, right? And the expected value of the product of so-called independent random numbers, we are testing it after all right now, but assuming that they are independent, the expected value of their product, or the average value of the product of the consecutive numbers, should be very close to 0.25, right? Because after all, each of them has 0.5 expectation, and we know the expected value of the product of random values is equal to the product of the individual expectations if they are independent. So if the expected values are 0.5, and if they are independent, so the expected value of the product of consecutive numbers should be very close to 0.25. So you calculate this value and take the average of them. You sum these values up and take the average of them. The value should be very close to 0.25 if the sequence is really independent. But of course, this is just a statistic. After all, there will be some deviation. So for an independent subsequence, we expect this value to be close to 0 because we are subtracting 0.25 here. Now, we also need to calculate the theoretical standard deviation of this autocorrelation. So this autocorrelation is normally distributed according to this formulation, because this is basically a sum of random values and the average of random values. You know, according to the central limit theorem, the sum or the average of independent random values is normally distributed. And we need to determine the standard deviation for this normally distributed statistical estimate, which is just equal to square root of 13m plus 7 divided by 12m plus 12. Then we are going to divide the statistical estimate for the autocorrelation to the standard deviation, and that is going to be our test statistic Z0. Now, if this Z0 is greater than the critical Z value that we identify from the cumulative distribution of the standard normal table, then we will say that there is enough evidence of dependence. The subsequence shows a dependence relation. Therefore, we reject the null hypothesis. So how do we determine the critical value? The critical value is basically 1 minus alpha over 2% quantile of the standard normal distribution. So from the CDF table for the standard normal distribution, we need to identify the inverse CDF at 1 minus alpha over 2, where alpha is your significance level for the statistical process testing procedure. And if the absolute value of your test statistic is greater than this value, then you reject the null hypothesis and conclude that there is a statistical dependence in the subsequence, and you reject the sequence itself. You wouldn't use that in a simulation. But if the test statistics absolute value is less than or equal to this critical Z value, then you will say that there is not enough evidence to reject the null hypothesis. The subsequence seems to show no dependence relation. It seems to be independent, you would say. Now let's practice this testing procedure in this final example. So we have this random number sequence that consists of 30 numbers. Now you realize that we have already told you that at every fifth number we observe a large value, but actually we are not going to test this subsequence. Instead, in the question, it tells us we need to check the autocorrelation within the proper subsequence, starting from the third index and moving ahead at every fifth index. which is basically trying to check the autocorrelation of 3.35, so row 35. So null hypothesis states that this is equal to 0, and the alternative hypothesis states that this is different than 0. And we are going to use a significance level of 0.05. Now, if you are going to create a subsequence from an original sequence of 30 random numbers, this is just going to have 6 observations, right? So starting from the third index, 3, 8, 3, 8, 3, 8. So you are just going to have a sequence of 6 numbers here. And for a sequence of 6 numbers here, choosing a significance level such as 0.05 is not a good idea. Actually, it should be greater, right? So for limited amount of data, always choose larger significance levels. Now, first of all, we need to determine the capital M value. And the capital M value is basically the largest integer that solves this inequality. And there is also another rule here. The capital M is always 2 less than the length of the subsequence. So we know that for subsequence here, starting from R3, it will end at R28, and it will consist of 6 random numbers only, and therefore M should be equal to 4. Then we are going to estimate row 35. So we are just going to multiply every consecutive random number in the subsequence. So we multiply 0.23 with 0.28. 0.28 will be multiplied with 0.33. 0.33 will be multiplied with 0.27. 27 will be multiplied by 0.05. And 0.05 will be multiplied by 0.36. Now, this is exactly what we are doing here. So how many multiplications are we doing with a sequence of 6 random numbers? There will be 5, right? There will be 5 consecutive couplings. And we are dividing the sum of the products to 5 and subtract 0.25. And the difference is minus 0.1945. Okay. Then the theoretical standard deviation for this autocorrelation estimate will also be calculated by the indicated formula here, which will be 0.1280 for the capital M value of 4. And the test statistic will be the division of the autocorrelation estimate to this theoretical standard deviation, and that is minus 1.516. Now, what we need to do is we need to check the 97.5% quantile of the standard normal distribution, because our significance level is 0.05, and we need to keep half of this probability on the right-hand side, the other half on the left-hand side of the symmetric distribution. And actually, if you remember your knowledge from probability theory and statistics, you would know that the 97.5% quantile of the standard normal distribution is equal to 1.96 approximately. And you see the absolute value of our test statistic is less than this critical value. So we conclude that there is not enough evidence to reject the null hypothesis here. The subsequence seems to show no dependence relation. So the test has passed, and we couldn't have found any statistical evidence to show that there is a dependence within this subsequence. Okay, that's the story of the autocorrelation testing. Actually, you can check other autocorrelations for other subsequences as well. As we have said, we should not go fishing for autocorrelation. So we should only check what we have a doubt about. So if you consider that there is a certain pattern within a proper subsequence, then you need to apply the test. However, if you do not have any doubt about it, why should you go for fishing for autocorrelation? Why should you test the autocorrelation of every proper subsequence? Because this is a infinitely long procedure. And as I have said, at some point, one test is just going to reject the null hypothesis. And does this mean really you need to throw away everything in the waste basket? Actually, it is not. We should not apply so much autocorrelation tests. So remember now, with a 0.05 or 0.05 level of significance, 1 out of 20 hypothesis tests are expected to reject the null hypothesis. I mean, that is the story of statistics. So, as I have said, maybe it is a good idea to check the row 1, the autocorrelation of the original sequence, and that's it. Okay, the rest is maybe not necessary.